Here's a lesson on collecting like terms. In part 1 of this lesson, let me start by explaining to you what like terms are. And remember, a term is just an expression formed by the product of numbers and variables. So for example, the product of 10 and x cubed would make the term 10x cubed. But what we want to focus on this lesson are like terms, which are terms that contain the exact same variables with the exact same exponents. So let's have a look at these two boxes here so we can carefully analyze what makes terms like terms versus what makes them not like terms. Looking at the box on the left, I see two terms that are like terms. 3x to the 4 and negative 2x to the 4 are both like terms. Even though the coefficients, 3 and negative 2, are different, the coefficients don't matter when deciding if terms are like terms or not. We just look at the variable part of the terms. The variable parts on both terms are x to the power of 4, the same variable with the same exponent, which is what makes those terms like terms. Whereas if we look at the box on the right, the two terms, 5x to the power of 7 and 5x to the power of 3, although the coefficients are the same, once again, that doesn't matter when deciding if terms are like terms or not. All we look at is the variable part of those terms. And although they both have an x, the exponents are different. One is 7 and one is 3, which is what makes those terms not like terms. And I just added a note at the bottom there underneath the boxes that says, notice that the coefficients of the variables do not need to match for the terms to be considered like terms. We just look at the variable part and make sure they have the same variables with the same exponents. So let's go ahead and try example 1, where we just identify the pair of like terms in each expression. In part A, I have 1, 2, 3, 4, 5 terms. Are any of them like terms? Well, I have two constants, 7 and negative 1. Any constants are like terms because they don't even have a variable part to their terms. So 7 and negative 1 are like terms. And that's the only pair of like terms here. If we look at the other three terms, 3x, 3y, and 2xy, none of them have the exact same variable part. The 3x just has an x, the 3y just has a y, and the 2xy has both an x and a y. So none of those variable parts are exactly the same, so none of those three are like terms. And now let's try part B. Looking for terms that have the exact same variables with the exact same exponents, I see that I have a negative 4xy and a positive 6xy. Those are like terms because the variable parts are exactly the same, xy, xy. So those are like terms. And then none of these three other terms have a like term. There are no other terms that have the exact same variable parts. Although the 2x squared y has both an x and a y, the x has an exponent of 2 on it. Whereas these two terms, the x's only had an exponent of 1 on it, which is why this 2x squared y is not a like term with them. And now let's move on to the next part of the lesson, where we learn how to collect like terms. Collecting like terms allows us to simplify algebraic expressions and make them shorter and easier to work with. When adding and subtracting like terms, they can be combined by adding or subtracting their coefficients and keeping the variables exactly the same. And note that only like terms can be combined together by adding or subtracting. For example, 3x plus 4x, because those are like terms, they both have an x, we can combine them together by adding their coefficients of 3 and 4 to make 7, and then keeping the variable part exactly the same, keep it as x. But if we look at 3x plus 4x squared, there is no way to combine those two together because they're not like terms. The variable parts are different. The 3 has an x to the 1, where the 4 has an x to the 2. Because the exponents are different, they're not like terms, and they cannot be combined. So let's go to example 2, where we practice combining like terms together. It says simplify each expression by collecting like terms. Well, part A is the example we already did together. Notice they're like terms, the variable parts are exactly the same, so I can collect them together by adding their coefficients of 3 and 4 to get 7, and keeping that variable part the same, keeping it as x. So hopefully that would make sense that if you have 3 x's and you add 4 x's, you now have 7 x's. Looking at part B, I now have 3 terms. 1, 2, 3, right? They're separated by the addition operators. The first two terms, 3x squared and 5x squared, are like terms because their variable parts are exactly the same. They both have an x with an exponent of 2. So I can collect those like terms together by adding their coefficients. 3 plus 5 is 8. And then keep the variable part exactly the same. Keep the x and keep the exponent as 2. And then I also have this constant term of 3, which is not a like term with that 8x squared, so I cannot collect them together, making 8x squared plus 3 my final simplified expression. Moving on to part C, I now have 1, 2, 3, 4, 5 terms. Let's look for pairs of like terms. I have a 2b, a negative 1b, and a 3b. Those all have the exact same variable part. They all have a b to the power of 1. So I'll highlight those three. And then the constants of 7 and negative 8 are also like terms because they don't have a variable part. Any constants are like terms with each other. And now let me rewrite this expression with the like terms beside each other. When I rearranged this, notice for each of the terms, like for example this 8, the sign to the left of it, so that negative sign stays with that 8. We think of it as a negative 8. Whatever sign is to the left of a term stays with it when we rearrange it. And now collecting my pairs of like terms, the first three are like terms. I have 2b minus 1b, right? If you don't see a coefficient in front of a variable, it's 1. So I have 2b minus 1b plus 3b. To collect those like terms, I just add or subtract the coefficients. 2 minus 1 is 1, plus 3 is 4. So that gives me 4, and then keep the variable part the same. It gives me 4b. And then my constant terms, I have 7 minus 8, which is negative 1. So there's my final simplified expression. And for any question where you're simplifying an expression, one way to check if you did it right, well, we're stating that the original expression is equal to 4b minus 1. We can check if it's equal by subbing in a test value for b into both the original and the final simplified expression and make sure we get the same answer. So for example, I could test what if b was 2. If I rewrite the original expression but change all the b's to 2, I would have 4 minus 2, which is 2, plus 7, which is 9, minus 8, which is 1, plus 6, which is 7. And if I sub 2 into my final simplified expression, I would have 4 times 2 minus 1, which is 8 minus 1, which is also 7. So notice both the original and the simplified both gave a result of 7. Now, technically, that doesn't prove that they're equal for all values of b. It only proves that it's true for b equals 2, but it's a good starting point to verify that we're not clearly wrong with what we got. Okay, let's move on to part D. With part D, let's start by looking for like terms. The first term has a variable part of x squared. I see the last term, this negative 3x squared, also has a variable part of x squared. So that pair are like terms. I'll highlight those the same color. And then I have a negative 6x plus a 9x. They both have an x to the power of 1. So those are like terms. And then I have the constant of 2. There are no other constants, so there'll be nothing I can collect with that 2. Let me start by rewriting this with the like terms beside each other. So I'll put the 3x squared and the negative 3x squared together, and then the negative 6x plus the 9x together, and then the constant of positive 2. And then notice this term here, the negative 6x. That negative that's to the left of the 6x, when we rearrange it, it stays with that 6x. Now collecting the like terms, I have 3x squared minus 3x squared, which is 0x squared, which is just 0. So I don't have to write that. They cancel out. But collecting negative 6x plus 9x, adding their coefficients, negative 6 plus 9 is 3, and then keep the variable part x, and then plus that constant of 2. And that's my simplified final expression. I can't collect 3x and 2 together because they're not like terms. Now let's do 2 more. Part E, looking for like terms. The only like terms I see are the negative 3y squared and the positive 2y squared. The variable parts of both of those terms are y squared. Of the 3 remaining terms, none of them are like terms with each other. This one has an x to the power of 2, while this one has an x to the power of 3, and this has both an x and a y. The variable parts are not the same. So I'll rewrite this with my like terms together, and I'm actually going to write this in descending order of degree. This negative 8x cubed is my highest degree term, so we should start our expression with that highest degree term, the negative 8x cubed. And then the 4 remaining terms are all degree 2. When they're all the same degree, the order doesn't really matter. But usually what we do is we then just base it off of the exponents on the x. So the 2x squared has the highest exponent on an x, so I'll put that one next. And then the xy has an exponent of 1 on the x. That will come next. And then my like terms, negative 3y squared and positive 2y squared, don't have an x, so I'll put them last. And then simplifying this expression, all I can do is collect those two like terms that are at the end. The coefficients are negative 3 and positive 2. Negative 3 plus 2 is negative 1, so these two will collect together to negative 1y squared. And when the coefficient is 1 or negative 1, you don't have to write the 1. We can just write minus y squared. And then because none of these four terms are like terms, I can't collect any of them together, so that's my final simplified answer. And then moving on to part F, let's start by looking for any like terms that we have. I see an a squared b plus another a squared b. Those are like terms. They both have an a to the power of 2 and a b to the power of 1. I have a 2ab and a negative 3ab. Those are like terms. They both have an a to the 1 and a b to the 1. And then the middle two terms are also like terms as well. They both have an a to the 1 and a b to the power of 2. So I'll rewrite this with the like terms beside each other. And to put them in the proper order, just like I talked about for the last one, let's look at this note on the side. It says the degree of the terms should be in descending order. Highest degree terms go on the left, and then they go in descending order as we move to the right. Well, the highest degree terms, both the yellow terms and the green terms, are degree 3, right? If we add the exponents on the variables, it's both 3. So to decide between the two, we'll look at the variable a. Which ones has a higher exponent on the a? And it's the a squared b terms. So they'll go first. And then the green terms, which are also degree 3, but only have exponents of 1 on the a, they'll go next. And lastly, the blue terms, 2ab and negative 3ab, they'll go last because they're just degree 2. And now I can collect all my pairs of like terms. The a squared b's both have coefficients of 1. Adding those ones together, I get 2, and I leave the variable part exactly the same. It stays as a squared b. Looking at the middle two terms, I have a negative 1ab squared plus a 2ab squared. Negative 1 plus 2 is positive 1. So the coefficient becomes positive 1, and keep the variable part exactly the same. Keep it as ab squared. And then the last two terms, I have a 2ab minus a 3ab. 2 minus 3 is negative 1, and keep the variable part the same as ab. And remember, when we have a coefficient of 1 or negative 1, we don't have to write the 1. And this is my fully simplified answer, because none of these three terms are like terms, because the exponents on the variables do not match, which means I can't collect them together. And now let's do one final question where we try and apply our understanding of how to collect like terms. Part A says write an expression in simplest form for the perimeter of this shape. Well, the perimeter would just be equal to the sum of the lengths of all four sides of this shape. And these tick marks mean that both of those sides are the exact same length. They're both 3x plus 5. So to get a simplified expression, I just need to add all of these lengths together and collect like terms. So I'll start by writing the sum of those four sides. And now I'll look for the like terms. Well, I have 1, 2, 3, 4 terms that all have the exact same variable x to the power of 1. So those are all like terms. And then I also have 4 constants. Those are like terms as well. So I'll start by rewriting this expression with the like terms beside each other, putting all the terms with an x to the 1 first because they're degree 1. They're higher degree than the constants, which are all degree 0. And now I'll collect my like terms, the first 4 terms. If I add the coefficients, 18 plus 3 is 21, plus 3 is 24, plus 9 is 33. So the coefficient of the collected terms is 33, and the variable part stays the exact same. It stays as an x to the power of 1. And then collecting my constant terms together, 7 plus 5 is 12, plus another 5 is 17, minus 2 is 15. It's a positive 15, so I write plus 15. So this is my simplified expression. 33x plus 15 gives me the perimeter of this shape. And now let's evaluate this expression, so find the perimeter, if x is 5. So I'll rewrite the expression for the perimeter, but change the x to 5, which gives me 165 plus 15, which gives a final perimeter of 180. And we don't have what unit of measurement we're in, so I'll just put units. So hopefully that lesson was helpful and you now understand how to collect like terms together. make sure you go to jensenmath.ca and get the worksheet that goes along with this lesson and try out the practice questions.
Jensen Math!